Hi everyone. Uh, I'm going to post a few brief videos on how to solve applied optimization problems using analysis of the first derivative. And this will be the first such video of the sequence. Now such problems, they can be challenging to solve as each one is quite unique. However, we can outline a general solution strategy. So the first thing you would want to do is to identify all the relevant variables in your problem. For instance, if you have a problem involving the volume or surface area of a solid, then the dimensions of your solid would be significant variables in your problem. You want to get a feel for the extremes of the situation by determining the ranges of your variables. So are there upper and lower bounds that are necessarily imposed by the physics of the situation, for instance? Could you write down equations that relate the variables? Of course, at least one of your equations must involve Q, where Q represents the quantity to be optimized, to be maximized or minimized. You'd like to try to express Q as a function ultimately of only one of the other variables, say the variable X. Then once you've done that, right, which is the hard part of the problem, then the rest just becomes calculus. Okay, differentiate Q with respect to X and find the critical numbers. Evaluate Q at these critical numbers and at the endpoints of the domain of Q if applicable. Obviously, if Q is unbounded, there may be no endpoints to worry about, or the domain may be an open interval again, so the endpoints aren't included in the domain. So after evaluating Q at all of these relevant points, then you could select from them the maximum or minimum value as needed. So this is just a general, again, solution strategy, which we would like to apply in several problems. And we'll look at one in this video. So the question we begin with is to find the coordinates of the point Q that lies in the first quadrant along the graph of y squared equals x, that is in fact nearest to the point 2, 0. So the first step in such a problem would be to graph a picture of the curve and the point P and a possible location for the point Q. Okay, so we'll begin with drawing our XY plane. Okay, and so we'll scale our x-axis a little bit. Say we go at least out to say 4 on x. Okay, and y here going up to 2 and say down to -2. And of course, we know that this graph is a parabola that opens to its side, to the right, with vertex at the origin. You could see if x is 1, then y squared is 1, so y is plus or minus 1 when x is 1. And if x were 4, y squared would be 4, so y is 2 or -2. And so therefore, you could kind of locate these points, several points now, on your graph. You could also see if x was, say, 1/4, then y would be either 1/2 or -1/2. And so now we have, several points, and we could try to use them to draw a nice picture of the parabola here opening to its side. Okay, so there it is. Now, Q is a point that's along the parabola and also in the first quadrant. So we could select sort of an arbitrary point on that upper branch. Say we take this point, for instance. Say this is going to be our generic point Q, X, Y. Okay. Now we want to minimize the distance from Q to P, which is the fixed point, to 0. Okay. So what do we have is we have this line segment PQ of some length, let's just call it capital D, to represent the distance from P to Q. So we said that Q equal to XY, Q equals XY, and the distance from P to Q is given by D, which according to the distance formula, right, we would take the square root of the change in x minus 2 squared, plus the change in y minus 0 squared. Okay, thus we have, let me push my paper up here a little bit. The distance is the square root of x minus 2 squared plus y squared. Okay, so that's a formula for the distance from the point P to Q. Now, the only thing is, D is given as a function of two variables, x and y. And in order to apply our derivative analysis, we need to have D a function of only one variable. But remember that Q was restricted to be a point in the first quadrant. So we know that along the branch of the parabola in the first quadrant, y must be positive, right? Y is positive, right? And so y squared equals x requires that y is the positive square root of x. Okay, and so we'll kind of keep this equation here in a box. We have our distance from P to Q here, which was well known. And so let's call this equation 1, this equation 2. So now we could substitute for y from 2 into 1. Let me push up my paper here a little further. So now substitute for y from 2 into 1 to find that the formula for distance, now just as a function of x, would be the square root of x minus 2 squared plus, and then, the square root of x squared. Okay, and we know, of course, we were talking about the ranges of the variables, right? Because x represents the x coordinate of Q. Q is in the first quadrant. Therefore, x must be positive in the first quadrant, right? So the domain of x is all positive numbers in this formula for the distance from P to Q. And of course, we could simplify this formula a little further if we simply expand under the radical sign. We would have x squared minus 4x plus 4 plus x. Okay, and so therefore, let's write it over here now. Our distance formula, d of x, therefore reduces to the x squared, okay, minus 4x plus x is going to give you a minus 3x plus 4, and then the square root is also to the power 1/2. Okay, x squared minus 3x plus 4 to the power 1/2. And thus we could differentiate to find d prime of x to be half times our base function, right, by the chain rule, half times the base function to the power minus 1/2. and then times the derivative of the base, 2x minus 3. And thus, the formula for d prime of x would reduce to 2x minus 3 divided by 2 times the square root of x squared minus 3x plus 4. Okay, so that would be our formula for the derivative. We notice that remember that this quantity under this quantity in the denominator, the square root of x squared minus 3x plus 4, represented the distance from P to Q, which we knew was always positive, right? So the denominator will never be 0 for any positive value of x. And therefore, the only critical number would occur when the numerator is 0. And of course, that means that 2x minus 3 is 0. 2x is equal to 3, or x is 3 over 2. Okay, so 3 over 2, therefore, is going to be our only critical number for this distance function. And we remember that when we found our critical numbers, we used them to split our domain of the function into subintervals. So we had the domain was the positive half of the x-axis, okay? And so here's, say, it's going to be 3 halves on the x-axis. So, it splits our half line into 2 subintervals here. And we could check out, so here's our d prime of x, right? This is given by this formula. Right? We notice that if we substitute in any value of x between 0 and 3 halves, say 1 for instance, the numerator would be like 2 minus 3 minus 1 would be negative. Remember, the denominator is always positive for all positive x's. So negative over a positive is negative. So d prime is negative here. So that means that the slope to the graph of the distance function d of x is negative, which means, right, that d is decreasing, okay, on the interval from 0 to 3 halves due to the negative slope to its graph. However, once x exceeds 3 halves, say x was 2, right, then evaluating the derivative at 2, we would get like now 4 minus 3 in the numerator, or a positive numerator, which will make the whole derivative positive valued. So the derivative is going to be positive on the interval 3 halves to infinity. That means that the distance function d always has positive slope, so it is in fact increasing on the interval from 3 halves to infinity. And so we know that by our first derivative test, right, if the derivative is negative on the left side of the point, then positive on the right side of the point, right, the function had to bottom out at the critical number. So therefore, d is minimized when x is 3 halves. So therefore, yeah, we'll just write here, d is minimized when x equals to 3 halves. And so the coordinates, so now we should say, so what are the coordinates of q, the point on the graph of the parabola in the first quadrant that's nearest to point P. So q would have the x coordinate 3 halves. Remember that y was going to be the positive square root of x at point q. So therefore y is necessarily the square root of 3 halves. So this is in fact the point on the parabola, right, nearest to P in the first quadrant. So again, just to summarize what we did, right, we drew a picture to illustrate our situation. we wrote down the distance formula from P to Q. We saw that we could express the distance formula as a function of only x by using the fact that y is the square root of x. And so then upon making that substitution into our distance formula, we ended up with this formula, which again was simply a function of x, which using the chain rule, we differentiated, we found the critical number, we used the critical number to split the domain of D into two subintervals, and then we were able to establish using the first derivative test that indeed D achieves a minimum value at the critical number x equals 3/2. Therefore, Q has these coordinates. So that was just one example. We'll do several more very soon. So let me know what you thought of this example. Thanks for watching it. Goodbye.